2.3. The precise definition of a limit. The outline of this video is as follows. We will begin by introducing the formal, precise definition of a limit, which is known as the epsilon-delta definition, providing the rigorous foundation for everything we do with limits. Once we understand the definition, I will show you how to apply it to carefully verify specific limit statements, moving beyond just intuition. From there, we will develop the practical algebraic methods for finding a suitable delta value for any given epsilon challenge, which is the core skill for working with this definition. To conclude, we will see how this powerful tool is used not just for individual problems, but to formally prove the fundamental limit theorems, such as the sum rule, that we rely on for everyday calculations. This journey will take us from the abstract definition to its practical and theoretical power. To make our understanding of limits rigorous, we need to move from intuition to a precise definition that we can use for proofs. The central idea is to show that we can make the gap between a function's value, f of x, and its limit, L, as small as we want, simply by keeping x close enough to a point C. For example, let us consider the function y equals 2x minus 1 near x equals 4, where the limit is 7. If we want our output y to be within 2 units of 7, how close must x be to 4? This means we want the absolute value of the quantity y minus 7 to be less than 2. By substituting the function, this becomes the absolute value of 2, x minus 8 is less than 2. Solving this inequality reveals that x must be between 3 and 5. This shows that keeping x within 1 unit of 4 guarantees our function's output stays within 2 units of 7. To make the idea of a limit rigorous, we need a method that can handle any error tolerance, no matter how small. We can think of this as a game between a skeptic and a scholar. First, the skeptic challenges us by providing a small, positive error tolerance, which we call epsilon. This sets a target range for our function's output around the limit L. Our job as the scholar is to respond with a positive distance, which we call delta, around the input value C. We win the round if keeping our input x within this delta distance of C guarantees that the function's output, f of x, stays within the epsilon tolerance of L. For instance, the skeptic might demand an error smaller than 1/1000th. The only way to formally prove the limit is to show we have a method that can find a successful delta for every single epsilon the skeptic could possibly choose. Now I will formalize our intuitive idea of a limit with its precise mathematical definition, which provides a rigorous way to test a potential limit value. We say the limit of a function f of x as x approaches c is the number L if a specific condition can always be met. For any positive error tolerance you can name, no matter how small, which we call epsilon, there must exist a corresponding positive distance around CLIAC, which we call delta. This guarantees that if we choose an input x that is within this delta distance of c, but not equal to c, then the output f of x will be within the epsilon tolerance of the limit L. For example, epsilon could be the required 1 mm precision for a machine part, and delta is how tightly you must control your cutting tool to achieve it. The key is that the value of delta you need almost always depends on the epsilon you are given. This definition allows us to prove that a function truly approaches a specific limit. Let us visualize what the formal definition of a limit really means. The core idea is a challenge and response game for controlling a function's output. First, you challenge me by setting a desired output tolerance, which is the horizontal band of width 2 epsilon centered on the limit L. My task is to respond by finding an input tolerance, which is the vertical band of width 2 delta around the value C, that is narrow enough to trap the function's graph. If I can find a delta so that for any x in the vertical band, the function's output stays within your horizontal epsilon band, I have met the challenge. Note that what happens exactly at x equals c itself does not affect the limit. The essential point is that for the limit to exist, I must be able to win this game for any epsilon you choose, no matter how tiny. Now I will use the formal definition of a limit to prove that the limit of the function 5x minus 3 as x approaches 1 is indeed 2. This process shows how we can find a specific relationship between our output tolerance, epsilon, and our required input tolerance, delta. We begin with the condition we want to satisfy. The absolute value of our function minus the limit must be less than any given epsilon. For this problem, that is, the absolute value of the quantity 5x minus 3 minus 2 is less than epsilon. By simplifying the expression inside the absolute value, we get the absolute value of 5x minus 5, which we can then factor into 5 times the absolute value of x minus 1. This algebraic step reveals the direct link we need. To guarantee the whole expression is less than epsilon, we just need to make the absolute value of x minus 1 less than epsilon divided by 5. So by choosing our delta to be epsilon divided by 5, we have proven that the limit is 2. Let us use our formal definition to prove 2 foundational limits that confirm our intuition. First, I will show that the limit of x as x approaches c is simply c. The definition requires us to ensure the distance between our function value, which is x, and the limit, c, is less than some positive epsilon. This means we need the absolute value of x minus c to be less than epsilon. Since this is the very same condition we control with delta, we can simply choose our delta to be equal to epsilon, and the proof is complete. Second, let us prove the limit of a constant function, k is k. Here, we need the absolute value of k minus k to be less than epsilon. This simplifies to 0 is less than epsilon, which is always true for any positive epsilon. Therefore, any positive delta will work because the function's value never deviates from its limit. These proofs show how the rigorous definition works for simple, intuitive cases. This two-step process provides a reliable algebraic method for finding a suitable delta for any given epsilon. We begin by working backwards from the condition that the absolute value of the quantity f of x minus L must be less than epsilon. Solving this inequality for x will give us an open interval of input values, from a to b, that produces the desired outputs near the limit. The second step is to place a symmetric interval around our point C that is guaranteed to fit inside the interval from a to b. Because the interval from a to b might not be centered on C, we must choose delta to be the smaller of the two distances from a to the endpoints. For example, if C is at 4, and the interval is from 2 to 9, the distance to 2 is 2, and the distance to 9 is 5, so our delta must be 2 or less. This method ensures our delta interval never extends beyond the bounds required by epsilon. Now let us see how to find a suitable delta when our function creates a non-symmetric interval for x, a common situation with nonlinear functions. We want to prove the limit of the square root of the quantity x minus 1 as x approaches 5 is 2 for a given epsilon of 1. First, we solve the inequality where the absolute value of our function minus the limit is less than 1. The algebra shows that this holds true for any x inside the open interval from 2 to 10. Our next step is to find a delta that places an interval centered at c equals 5 entirely inside this safe zone. The distance from our center 5 to the left endpoint 2 is 3, while the distance to the right endpoint 10 is 5. To ensure our delta interval remains within the bounds, we must choose the smaller of these two distances. Therefore, any positive delta less than or equal to 3 will work. Let us prove the limit for a function that has a different value, or a hole, at the point we are approaching. Our goal is to find a delta for any given epsilon. Because the limit definition requires that x does not equal 2, we can ignore the function's value of 1 at that point and simply use the rule f of x equals x squared. First, we solve the inequality, where the absolute value of x squared minus 4 is less than epsilon, to find the corresponding interval of x values. This gives us an open interval from the square root of the quantity 4 minus epsilon to the square root of the quantity 4 plus epsilon. Next, to guarantee our input neighborhood fits inside this target interval, we choose delta to be the minimum distance from our center, 2, to either of its endpoints. This safe choice of delta completes the proof, showing that a limit depends only on the function's behavior near a point, not the value at the point itself. The main reason we have the formal epsilon delta definition is not for calculating specific limits, but for rigorously proving the general limit laws we rely on. I'll now demonstrate this by outlining the proof for the sum rule, which says the limit of a sum is the sum of the individual limits. Our goal is to show that the distance between the function sum, f of x plus g of x, and the limit sum, L plus m, can be made smaller than any positive epsilon. The key step involves a clever tool called the triangle inequality, which let us break the problem into two simpler parts. It states that the total error is less than or equal to the error from f of x plus the error from g of x. Think of it like a total budget for error. If our total error must be less than epsilon, we can just require the error from each function to be less than epsilon over 2. This strategy allows us to prove the sum rule by controlling each function's behavior separately. To complete the proof, we need a single delta that keeps our combined error less than any given epsilon. The strategy is to split our total error tolerance, epsilon, in half, assigning 1/2 to each function's individual error. The definition of a limit guarantees we can find a delta 1 for f of x and a separate delta 2 for g of x that keep each function's error below epsilon over 2. Now, to ensure both of these conditions hold at the same time, we simply choose our final delta to be the minimum, or the smaller, of these two values. This choice ensures we satisfy the stricter requirement. For instance, if we need x to be within 0.1 for the first function and 0.01 for the second, choosing 0.01 works for both. With this single delta, the total error is less than epsilon over 2 plus epsilon over 2, which equals epsilon, and that completes the proof, showing the limit of a sum is the sum of the limits. To formalize the idea of a limit, we use a challenge and response framework based on two key values. The challenge begins with an error tolerance, which we call epsilon, that specifies how close the function's output must be to the limit value, L. Our response must be to find a corresponding distance, which we call delta, that defines an interval around the input value, c. The core relationship is that if our input x is within this delta distance of c without being equal to c, then the output f of x is guaranteed to be within the epsilon distance of L. For example, to keep a product's diameter within an epsilon of 1 millimeter, you must keep the machine's temperature within a delta of 0.5 degree. Ultimately, this rigorous definition is the foundation upon which all limit theorems are proven. To finish our discussion, I want you to reflect on two questions that get to the heart of the precise definition of a limit. First, consider the inequality that defines the input neighborhood. 0 is less than the absolute value of x minus c, which is less than delta. We know the second part of this inequality ensures x is close to c, but what is the significance of the first part, the condition that 0 is less than this absolute value? Think about what this requires of x relative to c. Second, let us recall the example where we examined the limit of the quantity 5x minus 3 as x approaches 1. If you are given an arbitrary output tolerance, epsilon, can you find a specific formula for the input tolerance, delta, in terms of that epsilon? Answering these will solidify your grasp of how delta depends on epsilon and why the value of the function at the limit point itself does not matter.